Section 4.2, the definite integral. Definition. If f is a function defined on the closed interval ab, we divide the interval ab into n subintervals of equal width delta x equal b minus a divided by n, and we let x not equal to a, then x1, x2, all the way to xn is b the endpoints of these subintervals, and we let x1 star, x2 star, all the way to xn star be any sample points in these subintervals. So xi star lies in the ith subinterval xi minus 1, comma xi. Then the definite integral of f from a to b is defined as this expression. I will explain this in later, provided that this limit exists and gives the same value of all possible choices of sample points. If it does exist, we say that f is integrable on closed interval ab. So let's look at the symbol, and then I will explain to you this definition. On the left hand side, we have this notation. This notation is look like an S, and it is called the integral sign. The whole thing, for this whole thing, the function f of x is called the integrand, and the a and b are called the limits of integration. A is the lower limit and b is the upper limit. The procedure of calculating an integral is called integration. On the right hand side, we have the notation of the sum, and that is called the Riemann sum, and it can be used to approximate the defined integral of an integrable function with any desired degree of accuracy. Okay, so let's explain this definition. So on the left hand side, this is the Riemann sum. In the Riemann sum, we are taking the sum of all of these rectangles. The width of these rectangles is a delta x. The endpoint A, we assign this is x0, and then x1, x2, x3, and then x4. So you learn in the section before, we can use the right endpoint or the left endpoint to calculate the area. So in this definition, they said that you can choose any x to be the height. To find the height, you just choose any x in the subinterval from xi minus 1 to xi. And that will be xi star. At xi star can be same as x3. It can be same as x4. For example, according to my picture, or it can be in the middle of x3, x4, or it can be anywhere. And when you take the sum of all these rectangles and you will take the limit, then the answer will be exactly the same as the area under the curve of the function f of x. And this is the integral of the function f of x from a to b. And also in this function, you can notice that all of the points of this function or this function is above the x-axis. So you say the function f of x is greater than or equal to 0. So what if the function f of x is not positive? It's not always above the x-axis. So look at the picture below. So there are two of them. So what if the function f of x that has some part that is above the x-axis, like the blue colors, and the yellow part is below? So in order to find the area, which is the blue and the yellow, we will add the blue together and then minus the yellow. So this could be A1 and this is A1. So we add the A1 together and then we will minus the A2. So A1 represents for the one above the x-axis, which is the f of x greater than or equal to 0, and the yellow represents for the part that below the x-axis, which is less than or equal to 0 for the function f of x. And this is the integral that we are using the other definition to find the area of the under the curve of the function f of x. So theorem number 3 and theorem number 4. So theorem number 3, before we read this, well, we know that we have defined a definite integral of an integrable function, but not all functions are integrable. We can see that in exercise 71 and 72. The following theorem shows that the most commonly occurring functions are in fact integrable. The theorem is proved in more advanced courses. Theorem 3. If f is continuous on closed interval AB, or if f has only a finite number of jump discontinuities, then f is integrable on AB, that is the definite integral from a to b of the function f of x exists. Now we have the theorem number 4, and this theorem is very similar to the definition. In this theorem, they are using the right-hand side because they are starting from I equal to 1, so you got x1. Okay, so you remember that we define A as x0, and if you plug in I equal to 1, then you got x1. So they are using the right endpoint in this theorem. However, we can change it to the left hand endpoint if we want, because we know that doesn't matter any point that we use for the rectangle to calculate the height, we will get the same answer anyway if you take the limit. So if you want to change it to the left endpoint, you can do like this. So you can change this to, you're gonna shift the n and the I to the left. Okay, so if you can start it from 0, which is give you x0, and that will be a, right? Yeah, you're gonna start a, and then the n is gonna be n minus 1. So you remember as b is xn, but we skip the b, so we use xn minus 1 if we want to use the left endpoint. Example number 1 is very easy. We will apply the theorem number 4. So the question is, we want to express this limit, which is the right hand side according to this theorem or the definition in the integral notation, and they give us the interval from 0 to pi. So here, so this gonna be your A and this gonna be your B. So we're gonna put A and B like this. This gonna be our function and no I. Okay, so will be x cubed plus x psi x parenthesis. So this whole thing here represent for this, but we just write f of x, right? So this is f of x and dx, and that's it. So they give us the Riemann sum, and we want to write in the integral notation for this.